are the Group 1.
And we're thrilled to present our exploration of the fascinating world of patterns and numbers found in nature.
Get ready to be amazed by the mathematical beauty that surrounds us.
Good day, everyone. So today we will be tackling about the 11 types of patterns and numbers in nature and the world. So first, we have symmetry, wherein it consists of 3 types. We have reflection symmetry, radial symmetry, and translation symmetry. But first, what is symmetry? So symmetry comes from a Greek word meaning to measure together and is widely used in the study of geometry. Mathematically, symmetry means that one shape becomes exactly like another when you move it in some way. Turn, flipped, or slide. For 2 objects to be symmetrical, they must be the same size and shape, with one object having different orientation from the first. There can also be symmetry in one object, such as a face. If you draw a line of symmetry down to the center of your face, you can see that the left side is a mirror image of the right side. But not all objects have symmetry. If an object is not symmetrical, it is called asymmetric. First, reflection symmetry. A reflection symmetry is a design has reflection symmetry if it can be folded along a line of symmetry, and both halves match perfectly. So, example. This image shows approximate reflection symmetry. If you were to draw a vertical line down the center of the halfway, the 2 sides would be roughly mirror image of each other, although not perfectly due to the slight variations in the architecture and the view outside. Next, or another example, is that this image shows approximate reflection symmetry. If you were to draw a vertical line down to the center of the display case, the 2 halves would be nearly mirror images of each other. The slight variations in the details of the individual items prevent it from being perfectly symmetrical. Next, the radial symmetry. So, the radial symmetry, a design is radially symmetrical if it can be rotated around a central point and still look the same. So, example. The wheel has radial symmetry because its spokes spread out from the center like rays of the sun. If you draw a line from the center to any point on the rim, the design on either side of the line is the same. Next is the air conditioner fan. So this shows radial symmetry because its blades or bars are arranged in concentric circles around a central point. So the pattern repeats outwards from the center. Next, the translation symmetry. A design has translation symmetry if it can be shifted, translated a certain distance and still look the same. So think of a repeating wallpaper pattern. So example, this image shows translation symmetry because the diamond pattern repeats itself by shifting horizontally and vertically. You could slide the pattern across or down and it would perfectly overlap itself. So another example. The image shows translation symmetry because the hexagonal pattern repeats itself by shifting horizontally and diagonally. If you move the pattern over, it would perfectly overlap itself. Next is we have spirals. So, a spiral is a curve which emanates from a point moving farther away as it revolves around a point. So, in the natural world, we find spirals in a DNA double helix, sunflowers, the path of draining water, weather patterns including hurricanes, galaxies, the horns of various animals, snail shells, ferns, and so on. So example, this image displays a coil spring which follows a helical or spiral shape. Spirals are continuous curves that wind around a central axis seen here in the spring's tightly wound structure. So this pattern is common in mechanical system to absorb shocks or store energy. So, another example. Is that this image shows a spiral pattern, as it features a threaded rod or screw-like structure. The helical threading follows a predictable, rational symmetry around a cylindrical object, which is a defining characteristic of spiral geometry in engineering and nature. Next is the meanders. The term meander is one which refers to a winding curve or bend in a river. Meanders are typical landforms at the middle and lower courses of a river. Meander gradients are usually more gentle and they experience lateral, sideways erosions which winding the channel of the river at the middle and lower courses of a river. So, example. The railing's design shows meanders because its vertical bars curve and winding, snake-like pattern rather than being straight. So another example is that this image shows meanders because the lines in the surface curve and bend in the winding sinuous pattern similar to a river path. Also, we have waves. So, a wave is a physical phenomenon characterized by its frequency, wavelength, and amplitude. In general, waves transfer energy from one location to another, in which case they have a velocity. Standing waves may also occur, thus have no net velocity and involve no net transfer of energy. They have frequency, wavelength, and amplitude. So mechanical waves require a medium to travel through. For example, sound waves and earthquake waves cannot travel through a vacuum. Electromagnetic waves such as light do not require a medium and can travel through a vacuum. Transverse waves such as light oscillate perpendicular to the direction the wave is carrying energy, and as in the diagram above. So the example is ocean waves. So ocean waves are a natural pattern because the constantly from due to the wind transferring energy to the water surface, creating wavy, the regular appearance. So this process emphasizes how energy and natural forces shape repeating design in nature. So another example is sand dunes. So our natural pattern formed by the winds consists actions on loose sand. So as wind blows, it picks up the sand particles and carries them until an obstacle, and also causes the sand to settle and accumulate. So the continuous influence of wind shape of this into regular wave-like patterns. So let's move to foams or bubbles. So a foam is a substance made by trapping air or gas bubbles inside a solid or liquid. Examples of foams formed by gases and liquids include sea foams, fire retardant foams, and soap bubbles. So another example that we provide is the bubbles in Coca-Cola. Exemplify the common natural phenomenon of gas released from a liquid, showcasing principles like surface tension and gasability. So these readily observable examples mirror similar bubbles formation processes found in various natural systems. So another example is the soap bubbles. So soap bubbles illustrate the principle of surface tension and gas entrapment within a liquid film, creating a visually appealing example of bubble formation. Next is the tessellation. So a tessellation is tiling that uses shapes to cover a surface with no gaps or overlaps. So picture a kitchen floor with tiles and you are looking at a tessellation. So this particular kitchen floor tessellation is made up of all squares. But tessellations aren't limited to just squares. They can be any shape or any combination of shapes. And the shapes don't have to follow a particular pattern. You can have a random tessellation of random shapes if you want it. And tessellations don't always have to be flat. They can also be three-dimensional, like when you take some building bricks and you make a wall or other solid structure with no gaps. So, examples. This image shows a tessellation because the floor tiles are arranged in a repeating pattern that covers the entire surface without gaps or overlaps. So the same design unit was repeated again and again. So another example is, this image shows a tessellation because the rectangular stone shapes fit together perfectly to cover the surface without any gaps or overlaps. So the pattern repeats regularly. Next is the fracture or cracks. So fracture occurs when the applied stress is sufficient to break the atomic bonds of the solid by Anderson of 1995 and Scholes of 2002, while crack is the propagation may be described using the energy criterion theory by Griffith of 1920, which is based on thermodynamic and energy balance. So, examples of fracture is the broken battle. So the battle broke into many pieces because something caused stress on the glass. So the broken edges are rough and uneven, which is what happens when something breaks easily. Another example is the eggshells. So this means they're broken into pieces because something put pressure or force on them, causing them to crack and split. So the examples of cracks are the tree trunk shows cracks in its bark. So these cracks are formed naturally as the tree grows and its bark expands and contracts. So they're a normal part of a tree aging process. So another example is, this picture shows dry ground with lots of cracks in it. So the soil has dried out and shrunk, causing it to split into many cracks. Next is the stripes and spots. So stripes are made by series of bonds or strips, often of the same width and color along the length. So nature's love of stripes and spots extends into the animal kingdom like tigers and leopards, zebras and giraffe. So examples. So this image shows a large model of a whale shark hanging from a ceiling of a store. So whale sharks have many spots on their bodies, so therefore the image belongs to the category of spots because of the shark's spotted pattern. So another example is this. So this image shows a model of a fish, likely array of similar species that has numerous small light-colored spots scattered across its body. So the presence of this stringed spots make it an example of something with spots. So let's proceed to the stripes. So here. So this image shows a pair of slippers with vertical stripes of two different colors, a light color and a darker gray or purple. So the parallel lines of construction colors are the defining characteristics of stripes. So this is also quotient features, parallel lines of alternating brown and cream colors running vertically across its surface. So this parallel lines of constructing colors are the defining characteristics of stripes. Next is the fractals. So a fractal is a never-ending pattern. Fractals are infinitely complex patterns that are self-similar across different scales. So they are created by repeating a simple process over and over in an ongoing feedback loop. So example. This image shows a tree with multiple branches or branching patterns. So fractal are self-similar structures that repeat at different scales. So just like how three branches divided into smaller branches and a repeating pattern. So this natural formation follows the concept of fractal geometry. So next example, the image shows a fractal-like pattern because the plant's branching structure repeats itself at smaller and smaller scales. So the overall shape is similar to the shape of individual branches, so which are in turn similar to the shape of even smaller parts. So it's a self-similar pattern. Also, we have affine transformation. So it is a linear mapping method that preserves points, straight lines, and planes. So the processes involved in affine transformation are rotation, reflection, and scaling. So a fern is an example of affine transformation because its fronds exhibit self-similarity with smaller versions of the same shapes repeating at different scales. So this demonstrates how affine transformation can describe the scaling, rotation, and translation of shapes, creating the intricate patterns and structures found in nature, like the fern's fronds. So another example is the cat cabbage. So the cat cabbage is an example of affine transformation because when you cut it, the veins and patterns within the cabbage remain straight and proportional, even though the shape of the cabbage has changed. So this illustrates how affine transformation preserves straight lines, so the veins, and ranges of distance, the patterns, even under transformation, like the cotton. So last but not the least, the Fibonacci sequence. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones, usually starting with 0 and 1 and continues 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. So this sequence is often found in nature, particularly in the arrangement of leaves, the branching of trees, and the patterns of flowers. So example. So these petals are arranged in a spiral pattern that follows the Fibonacci sequence, allowing for optimal packing and growth. So this mathematical principle enables the flower to maximize exposure to the sunlight and rain, while minimizing overlap between petals. So the Fibonacci sequence in this flower is the stunning example of how mathematics appears in the natural world, revealing the underlying order and harmony that exists in nature. So another example is the snail shell. So the snail shell is a remarkable embodiment of the Fibonacci sequence. So as the snail grows, it forms a spiral pattern that gets wider by the factor of the golden ratio, approximately 1.618 for each quarter turn. So this efficient arrangement enables the snail to protect its vulnerable body while using the least amount of energy and materials to build its shell.
And there you have it!
A journey through the breathtaking patterns and numbers woven into the fabric of our natural world. We hope we've shown you that mathematics isn't just about numbers on a page. It's the hidden language of the universe, whispering secrets in a spiral of a shell and a symmetry of a snowflake. So next time we're outside, take a closer look. You might be surprised by what you discover.
Thanks for watching from Group 1!